are an awe-inspiring reminder that through geological ages, ice has helped to sculpture the face of the Earth. Glaciers are today found chiefly in mountainous regions, but wherever water freezes, the ice contributes to this sculpturing process. Whenever water collects and freezes in rock crevices, it acts as a wedge powerfully driven into the fracture, for water expands as it freezes. Sooner or later, the wedge prizes loose parts of the rock. Freezing and thawing in open fields causes a new crop of loose rocks to be worked up to the surface each spring. In autumn, the lake water cools first at the surface. This colder water sinks because of its greater density. Circulation ceases when all the water has cooled to 39 degrees Fahrenheit, since the water is then at its maximum density. Further cooling at the surface causes expansion and consequently decreased density. Hence, the cold water remains at the surface and freezes. Even in severe winters, the greater portion of water under the ice does not cool below 39 degrees. Ice, like most solids, contracts when its temperature is lowered. This contraction opens up fissures in which additional ice is formed. Subsequently, when expanding during a thaw, the ice sheet becomes too large for the lake. Its edges are then pushed up on the beach, carrying gravel and rocks with them. When the ice melts, this debris is left high up on the shore. In high altitudes where the snowfall exceeds the melting, snow fields are found the year round. Snow consists of millions of individual snowflakes. With alternate freezing and thawing, the snowflakes are transformed into snow granules, such as these. Under pressure, these snow granules are changed to ice granules. The slightest slope beneath a snowfield causes the mass of granular ice to move slowly downward in response to the pull of gravity, thus forming a valley glacier. One explanation of glacial movement is that the intense pressure of millions of ice granules upon one another causes a temporary melting at their points of contact. This meltwater acts as a lubricant, and during refreezing, the rotary action of the granules, here shown greatly speeded up, aids in impelling the glacier downslope. Valley glaciers move down the most readily accessible depressions in river-like tongues of ice. This drawing of the surface of a valley glacier shows that its center is moving faster than its edges. The contact of the glacier with its bed retards the advance of the lower portions of the ice, as shown in this cross-section. This drag results in the shearing of the upper layers. From its bed and from overhanging cliffs, the glacier acquires great quantities of rock debris. This material may completely conceal the surface of the ice. The rocks in the bottom and sides scour the glacial bed. Scratched or striated surfaces are evidences of the work of these glacial tools. During warm weather, some of the surface ice is melted by the sun's heat. The water flows through small crevices, enlarging them as it plunges downward. Ice caves are the result of a long continuation of this process. The ice, melting to form such huge underglacial tunnels, yields great quantities of debris. When the glacier retreats, the material remains in long ridges called eskers. Soil and debris carried by water from such tunnels may spread out into alluvial deposits called valley trains. Here, with the action greatly speeded up, we see a glacier in which the rate of melting balances the rate of advance. Under such conditions, the ice margin remains almost stationary, and the glacial load of boulders, rocks, and soil is dropped at its front. This deposit is called a terminal moraine. Rocks, loosened by thawing, tumble down the front of the glacier and help build up glacial deposits. Steep-walled valley heads, called cirques, demonstrate the plucking power of ice at glacier heads. Here is a larger cirque, seen from the side. Glaciers also change their entire valleys to a characteristic U shape, so clearly illustrated in Yosemite Valley. An unglaciated V-shaped valley is seen downstream, beyond the moraine, which marks the farthest advance of the ice. This high waterfall marks the mouth of a hanging valley left far above a deep glacial gouge. Fjords are glaciated valleys, which are partially drowned by the sea. At least 1 million years ago, there began the latest of the Earth's many ice ages. Ice formed the western Cordilleran Glacier, the central Kuwaitan Sheet, and the Labradorian ice mass. The ice diverted the Missouri and Yellowstone rivers from Hudson Bay to the Mississippi. While the first ice sheet was melting, large lakes were forming in the Rocky Mountain region. Following this second glacial advance, called the Canson, the Missouri established its present course. A third advance, called the Illinoisan, altered the upper course of the Missouri River. During the fourth, or Wisconsin epoch, the Labradorian Sheet attained its maximum westward advance and extended to the present Lake Winnipeg area. There were several stages in the Wisconsin epoch. The positions of the fluctuating ice fronts are indicated today by the many moraines in the north-central states of America. About 18,000 years ago, when the ice retreated from the eastern end of Lake Erie, Niagara Falls came into being. Lakes Michigan and Erie, south of the glacier, first drained into the Mississippi River. Later, the combined Great Lakes drained eastward through the Mohawk and Hudson rivers. At this time, another large glacial lake called Agassiz occupied the Red River Valley. Later, the Great Lakes drained into the St. Lawrence, whose valley, together with Lake Champlain, was engulfed by the sea. With a further retreat of the ice, Lake Agassiz drained into Hudson Bay. Finally, when the land had risen after release from its great load, there came into existence what is essentially the present topography of North America. Today, two vast continental glaciers still persist. About the South Pole, the Antarctic ice cap, and in the northern hemisphere, the great Greenland ice sheet. The Greenland ice moves slowly outward into the sea, where it breaks off into huge chunks known as icebergs. This majestic iceberg, a mere glacial fragment, recalls ancient ice sheets and suggests future periods of climatic refrigeration in which ice will again change the face of the Earth.